Welcome back everyone. So last time we talked about tactic mode, and so this involved a bunch of tactics: exact, refine, apply, assumption, constructor, cases, some structuring cases, using case and bullets, some combinators, first, repeat, all goals, any goals, rewrite and simp, and some of the sort of heavy hitter tactics like ring, linear, and omega. Now, I know that was a lot of stuff, so if you have any questions about any of those things, if you were trying stuff out on your own, and you had questions, please feel free to ask. They will come back. We'll see more of these tactics in the future, and so we'll get some more practice with them in jobs. Okay. Some things. There were a few tactics that I wanted to introduce, which I forgot to mention, which I'll get to in a sec. And also, I did want to just sort of poll everyone here. Who has experience in using Agda before? Okay, almost everyone. Okay, so this is this is mainly just to calibrate, how much I should expect in terms of Agda style proof in what we're going to look at. So today we're going to be talking about inductive types. So pattern matching on inductive types, how you write inductive types, cases an induction tactic, some more tactics for dealing with nested case constructions called R cases, R and obtain, and then match expressions and no match. And then after the break, we'll cover structures and type classes. So that'll be good. Okay, so just for these simple, they're sort of combinator. They're really structural tactics. So I just want to introduce skip and fail. These are very simple tactics. Skip does nothing. You have a goal. In this case, our goal is to prove true. After skip, our goal is still to prove true. It does nothing. Normally, you don't use this tactic, and in fact, if we turn off these linters.
Is this already on the record?
Oh, excellent. Actually, thank you for reminding me. Let's put lecture 3.
You can press the buttons.
Okay. Sorry about that. Right, so, yeah, if I don't turn off these linters, I'll in fact get a warning that tells me that skip does nothing. So, just in case you had any other ideas. However, it's not completely useless. In particular, it is a tactic. So sometimes there are places where you're supposed to put a tactic, and if you just want to say, don't do anything, I don't have anything to do at that point, then skip is a way to do that. And it can also be used in these sort of higher order combinator things. But I also want to introduce fail. So fail is also very simple. Fail, fails. And you give it a optional expression, I think, yeah. So you don't have to give it a message, but you can. If you wanted to say, oh no, then it prints oh no. But one of the reasons why you might want to use these kinds of tactics is to control sort of higher order tactics. So here we have a try around a skip or a fail, and you can see this trace state. It prints out the goal state, but you can tell that this one's running and this one's not running because this one failed first. So this is just some rudimentary sort of control flow that you can control using things that fail. Okay. And done, I very briefly showed an example of it, but I didn't explicitly talk about it. So basically, done is a tactic which fails if there are goals. So an example where you would want to use it is like here. I wrote example, I want to prove true, I wrote by. And then I just wrote nothing after that. And you'll notice that Lena's super confused about the situation. It says like, it's highlighted, half of it, this example here and a bunch of stuff. It says unexpected token example. It's looking for a tactic, and I've written nothing, right? This is just the first half of an expression, and Lena's not giving me good information. So instead of doing that, when you're in that situation and you just want a nice clean error message that says this is your goal, and not Lena just being confused about what's what, then you use done here. And you can leave done in your, so you would just write other things before it. So after proving the goal, or like if you haven't proven the goal, then the done stays there, but as soon as you prove the goal, then done stops complaining, and we actually get this little light bulb here that pops up and says, what is it? Remove tactics after no goals, which will remove the done. So just, that's a nice cleanup thing, but you can always just delete it yourself. Alright, so onto the main topic. So inductive types are declared like this. So you say inductive, you give the name of the inductive, and here we're going to define an inductive called true, which has 3 states: true, false, and false. This is a shorter version of this definition. So like I can give it, I didn't say that has a type, but it does. And I can also highlight this and see that it has a type. And similarly, these constructors have the type true. So I can give their types here. When they're very complicated types, you will have to give it, but in this simple example, you don't. And that's how you define an inductive type. To use an inductive type, well, you can pattern match on it. For instance, if I want to, well, I guess the even simpler way to use an inductive type is just to construct one like this. So I call one of the constructors, in this case true, and it says, yes, that's a true. And then if I want to pattern match on one, then I have to give all the cases. So there are 3 different ways you can construct the true. So I pattern match on it. In this case, I'm going to turn it into a bool, but there's one of them that's sort of weird, so we're going to use an option bool. And so true maps to true, false maps to false, and false maps to none. Okay. And there's a couple other ways we can write this. Now this true dot true part is a bit annoying, so if we want to get rid of that, we can do the same thing inside the body of the namespace. And you'll notice, like, cool, this was working, but now this side is complaining. And it says, argument true has type true when it's supposed to be bool, because actually inside this namespace, we are basically referring to these things with their short names, but now true is overridden, sort of, and now we don't have access to the bool true. Question?
Is it possible to make guess which namespace to use based on the type?
Excellent question, and that, so there's several ways you can do this, actually. So I think, let me give one version of this. So if we have, instead of a namespace, we use open. Now we get an ambiguity. So there's a when you're resolving the name, the things that are in the namespace get priority over other names. So that's why in this namespace situation, this was unambiguously interpreted as true.true, even though both of them are in scope. So bool.true is already in scope under this name true, but this one's taking precedence because we're in the namespace. But when we use open, they're both in the namespace, but neither one of them is taking precedence, and so leave ours with a ambiguity. But if we wanted to have some more sort of intelligent resolving of which one is which, we can use, this is the usual way that I will handle that sort of thing. So you write this dot true, and what it does is it takes advantage of the fact that it knows that this thing is a bool in order to use bool dot true. There is actually a version of this that will just do type-based overloading, but I think for that you need to use actual notations and not just names. So I won't show how that works, but there is something. And of course you can refer to these things with their full names like this. So if you just say bool dot true. But what I normally do is, like, when I'm outside of the namespace, I can use these dot patterns in order to access the constructors of true without having to ever open it. And this is quite nice because there can be a lot of namespaces, and this saves you the trouble of having to open most of them most of the time. There is another thing that I wanted to mention here, which is, and you'll see it quite a bit in real code, which is to use protected. So I can say protected here, and now these fail to, so what this does is it says that you're never going to be able to use this by its short name. So the only way you can use true.true is using its full namespace name, or using this dot trick. The dot trick still works, but inside this scope, we still have to use the dots. And that saves that, so that would be a good idea to do in this case. I only did it for true and false because I happen to know that bool has true and false, and they're already in the namespace, so this is just going to cause problems when I'm in this namespace, as we saw. So now I think this will work as long as I do this. Right, so this is, even though we're inside this namespace, this is still resolving to bool.true. Okay, so that's just some namespace management stuff.
So indentation is not mandatory, or the names?
So indentation is, there are some aspects of indentation that are relevant to Lean, but like the precise amounts of indentation are not relevant, just whether things line up. So basically Python style. So like there will be cases where when you have a sequence of things in an order, all of the things have to line up with each other, but they can be indented or not. For instance, like here, I don't know actually whether these don't need to be in any particular indentation. Some people write it like this, some people write it like this. I think this is the MATLAB standard.
They prefer to use a tabs or choice space.
These are all two-space.
Okay.
Yeah. Yeah, you will not see tabs anywhere in Lean.
So in this namespace end block, you don't have to indent, and maybe it's similar.
Yeah. So you don't have to indent this, again, the style is not to indent around namespaces and sections, but you can sort of think of them as a big bracket. Okay. Inductive types can have parameters. These go before the colon. So, you don't have to have the colon here at all, but when you do, it comes before the colon. And this is just sort of held fixed for everything in the inductive type. So in this case, I'm defining an option type. Option has another type parameter, which is the thing that it's optional of. And it has two kinds of thing, there's none and some. So here I'm giving the types. Again, I don't have to. I can, even if I have a parameter, an argument to the constructor, I can put it here. And so that's defining option. And if I wanted to convert my option into an option, I can map none to none, some to some, and you can see again here I'm using this dot trick in order to avoid having to write open my option and then deal with the name clashes. Okay. Inductive types can also be recursive. So here's an example of list. So I've defined my list, which again has a type and it has a nil and a cons constructor. So nil is the empty list. Cons is you put the thing at the head of the list, and then the tail is another my list. So this should be somewhat familiar. And here we have, I was actually, well, so we can see here the way you can write a recursive function by just pattern matching on the elements of my list. So we have nil and cons cases, and here I want to say that a map of a list is, a map of nil is nil, and map of cons is a cons. And here I want a beta, so I have f applied to A, and here I want to apply map itself recursively. So that would be just f of b here. And after having done so, oh, and I should mention another thing about this namespace is actually sort of load varying here. You'll notice that it doesn't type check if I don't say the namespace, and you'll be like, whoa, why is that happening? And this is again because of name resolution. So here nil is in my list namespace, and when I write my list.map, it's actually basically equivalent to saying namespace my list around this definition. So like everything inside this def is resolved as though it were inside the namespace my list. So that's why I don't need to use the dot here. I can, but I don't need to use the dot around nil and cons, and it's not resolving to like list cons or something. Okay, and we can evaluate these things. So these have sort of compiler versions. So here we can evaluate that we write this my list expression here, and we get a list containing 1, 4, 0, and since I haven't set up anything in particular for pretty printing, I just get this sort of default thing, which says my 1, 4, 0, nil, and then here I can call this map function, and this funny syntax here is this is a vertical bar, a right arrow, and then a dot, and it looks slightly different because of the font, but this is applying the function map, which lives in the namespace of this expression here, which is my list. So that's how it figures out that I'm talking about my list map. I could also write that though as my list map like this, but then the arguments are in the wrong order. So there's this is just a convenient way of writing function application, again without having to write the namespace. So I mention these things mostly because it's incredibly common when you look in lean code in real life. And here, when we run this map, we multiply everything by 10, so we get 10, 40, 0. No surprises. Okay, so what does a inductive dictation actually do? So
this notation is a bit weird. So you have like the application operator and then dot.
Yeah, so
Without
the way you should parse this is these three characters, vertical bar, a right arrow, and then a dot, and then a identifier all have to come no spaces like this in one unit. And another version of this is you can skip this, but then it has to come directly after the expression with no space. So that doesn't work, but this does. And this is a sort of mixture of the pipe operator, which is like here you can see it's applying a function, but here we want to apply this function map, and we want to do it in an inferred namespace. And so this whole combination has been tied in this arrow dot rotation. Yeah, there's some syntax.
So it's funny that you can write this dot map even though the first argument of map is not a list, but
Right, yeah. So that's a good point. So when I use this syntax, I say it's like something dot map, and I have to figure out what. And so I look at the thing on the left, find out what namespace it's in, and then that tells me, oh, it's my list dot map. And then I look at my list dot map, and I look around. Does it have an argument that is a my list?
Mm-hmm.
And it does. It's not the first one. It's this one. So that becomes passed in as the mylist argument. And then all of the other arguments, like f here, get passed afterwards. So it's true, this actually does end up reversing the order of the arguments, but this is actually quite useful for being able to have the map function be written in the sort of Haskell-like order where you have the function and then a sort of functorial action. You know, being able to partially apply this is nice, but also you still get the ability to write it in this order.
If you just add a space between and then write mylist.map instead, it should do the same thing, I think.
If I do a space,
There, yeah, and mylist.
mylist dot map.
Ah,
Oh yeah, that's true. Maybe that's actually closer to what Haskell would do, right?
And now we don't need any reversal of order. to think about.
Right. Because, well, here, yeah, this is effectively doing the reversal. This pipe operator is doing the reversal function application. So yes, you're right.
And dropping the mylist doesn't work.
Dropping the mylist doesn't work. So when we have like I mentioned that this works with this, what it actually interprets this is this dot map is the same kind of dot as this here. So it would look at the return value. So like this expression has a certain expected type, except it doesn't really, because then this would have to be the argument to a function, and this would have to be a function, and it's not, it's a mylist. But if it was a function, then this would have an expected type, and it would use that to infer what namespace it should live in. So basically, this only makes sense for different kinds of scenarios, like constructing inductive types.
So this sort of namespace thing, I think I'm oversimplifying it in my head. It just seems like a way to avoid having to use like qualified function names and variables.
Yeah. I mean, at its core, that's all namespaces are ever about.
Okay. Just like this.
Yeah, you can if you wanted to write my list in all these places, then yeah, you absolutely could.
Okay.
All of these are my list, right? But yeah, especially when it comes to these sorts of things, there is a lot of namespace management that goes into just using like list libraries and so on. Okay, so what does an inductive declaration do? Well, it creates three main things, sort of four. One of them is a type. It creates a type, in this case called mylist. It creates the constructors. These are called nil and cons because I called them that. So basically, those are the three things that you can see obviously by looking at the expression itself. I have mylist, which is a type, nil, which is a mylist, cons, which is also a mylist, and then there's one more thing called a recursor. This was not completely obvious by looking at this definition. So we can actually look at what is this thing, this recursor, and it's effectively a function that does pattern matching on the type. So there's a bunch of things going on here, and let me sort of write them out myself so that it's a little bit clearer, maybe. So we have a motive here that represents some kind of type family that we're going to be constructing. We have an inhabitant of that motive at nil and another one at cons, where we assume that we have one at the tail and we have the head and the tail. So this is effectively a kind of induction, right? So we know that it's true at nil, and we know that if it's true at the tail, then it's true at a cons. Given that information, mylist.rec takes that and then it will produce for any mylist the motive applies to. So this is really what makes inductive types different from co-inductive types or other, like just being a fixed point. This is a least fixed point, so if something is true for nil and is true for cons, then it's true for everything. There is an error that's happening here when it's, I'm just applying mylist.rec, and it says code generator does not support recursor mylist rec yet. So if you ever see this error, you probably are missing a non-computable. So if I use non-computable section here, then the errors go away. But the short version of the explanation of what's going on here is that, well, the code generator does not support this recursor. It absolutely could, but there are some reasons why you might not want to use the recursor in actual code. So that's why the compiler prefers to have you use pattern matching instead, and it compiles it in a slightly different way. Okay. But so, under all this context, I want to show you what the final thing that you get out of. So these are constants. They don't have definitions. If you like try to unfold them or whatever, nothing will happen. They are just things that have a type. You know, my list is just a type, and my list.nil is just a thing that has this type. However, the recursor has a relationship to the constructors, and that relation is that if you have this recursor function and then you apply it to nil, then it is equal to the value that you get out originally. So this is, if you apply this function on nil, you get the first argument. And if you apply it on cons, then you get the second argument applied to the pieces of the cons and also on, and this is where the sort of inductive hypothesis went in. And these are both REFL, they're definitional equalities. So this is a reduction rule that tells Lean how to make use of an inductive type and sort of actually compute functions. So I want to do a demo of the using this recursor directly. And here I write list.rec in order to access the mylist.rec function and apply it to list, which is a mylist. And so basically what I want to do is rewrite this map function, but using using the recursor directly, right? So I have two things that I have to provide. One of them is a mylist of beta, and the other one is this function. So for the mylist of beta, this is essentially the nil case. So I have to give it a thing that has type mylist beta, and I know that the map of nil is nil. In the second case, I have been given the pieces of the list, and then I've also been given the inductive hypothesis, which is, in this case, the list that I would receive if I were to use it on the tail. So in this version of the function, I called map here. But actually what we're going to end up with here is not a recursive call to map prime at all. This is the whole purpose of this rec function is to make it so that you don't need to have recursion represented sort of implicitly with this name referring to itself kind of situation. So here we just need to apply cons, f of a, and the inductive hypothesis itself. Put that back.
So I'm a bit confused about the status of recursors. So internally they are not defined as by pattern matching, or?
Recursors are not internally, no, recursors are primitive. So that's like, these are the primitives that you get with an inductive type. When you write inductive, you get the type, the constructors, and the recursor, and the computation rules, and that's it. Pattern matching, and we can actually demonstrate this. If we look at my list map, we're gonna see that my list map was actually compiled down to something else. That is to say, like, during elaboration of this declaration, it figured out how to make a non-recursive definition. It's actually not using mylist.rec in here, it's using mylist.brec on, and this is part of how the compilation strategy works, but if I just keep unfolding these definitions, we'll eventually see it bottom out on calls to mylist.rec. And if I look at my list rec, there's no definition. This is actually the primitive. So from, at least from the point of view of the kernel, this is the primitive mylist.rec. From the point of view of the compiler, pattern matching is preferable, and it actually sort of intercepts some point between when it gets to the kernel and the text that you write. And so because it actually wants to see those pattern matches, and that because it's easier to use essentially a match and fix style of compilation strategy. And that's why it doesn't directly support mylist.rec or like run all of these things via their those unfoldings that I just showed, and why it complains when you use mylist.rec directly, because it sort of sidesteps that normally, but if you use it directly, then there's nothing it can do. Okay.
I see, but couldn't you, for the sake of the code generator, then allow? I mean,
Yeah.
Yeah,
and actually,
definition of rec or
yeah. In fact, I think I can demo
okay,
this.
you're going opposite ways, like
Yeah. So.
in terms of the kernel, you want to go towards the recursor. In terms of the compiler, you want to go towards the pattern matching. So
Well, you could take the recursor and then go to the pattern matching for the purposes of the compiler. And this is possible, and if I am trying to remember whether this actually exists. Compile, inductive. Well, I'm not about to look it up. But I believe there is a thing which I can tell it to compile my list as to basically give it the recursor. So then these will just work without the non-compute. This is the method, the extension. Okay. And okay, so I sort of already said this partially, but proofs by induction are also basically definitions by recursion. They're sort of the same mechanism to lean. So here I want to give an example of a theorem which I will prove by recursion, and this is sort of Agda style. So we define this function length, length of nil is 0, length of cons is the length of the tail plus 1. And then I want to prove that the length of map is the same as the length of the original list. And we do so by pattern matching. So here, our goal is actually, yeah, I can't actually see it, but the goal here is to prove map FL dot length is L dot length. And so I can pattern match on L, and then I get two sub goals. Okay, so just sort of filling out the holes here. The first goal is to prove that map f nil dot length is nil dot length, but because map f nil is defined to be nil, this is true by reflexivity. So I can prove that by REFL. And then here we have this other complicated thing. Map of a cons dot length is cons dot length. I can just assert that this is something plus 1, or yeah, something plus 1 equals something plus 1. Like so, and Lean has figured out what exactly it's supposed to be plus 1 of, but this is because if I just unfold map fcons, all this stuff, this is really saying this plus 1, because that's how we defined it. So if you unfold map and you unfold length, then you get this. So that means that I can use this conger arg with, so the conger arg is the theorem that says that if two things are equal, then applying the function to those two things are also equal. So in this case, I want to apply the successor function to both sides, and now I have to prove this map FL length. So this is our inductive hypothesis. I don't have an inductive hypothesis here, but I'm defining a function by recursion, so I can just call myself recursive on F and L, and that's a proof. and we actually don't need this part of the thing, because that's just for us basically to see what type the thing is. So this is how you can define a theorem, which is also sort of a recursive function. Okay. Yeah, question.
Yeah, so one thing that's just kind of confusing to me is the syntax of the dot, because it feels like, again, agda is just a projection from a record type, right? So here it's like overloaded to being both a kind of applying length. It's also for inductive types and for records, I suppose.
So it doesn't matter whether it's an inductive type or a record or a general type or anything, actually. This syntax in general just means find a function that has, so it's like when I write dot nil in this position, Lean is expecting me to write something whose type is the same as the type of L, so it's got to be a mylist A. And so when you write this dot and then dot something, and it's expecting a mylist, it will look in the mylist namespace. Is there a definition called mylist.nil? And there is. So it interprets this as, I guess you wanted to say mylist.nil. And now, for all the things that means, well, this is supposed to be one of the constructors. If this resolved to mylist, I could write my dot map here. And it sort of works. It works out that you meant mylist.map. But then it observes that mylist.map is not a constructor, so it shouldn't be showing up here. It's not complaining about list.map or nat.map or some other dot map. It has identified the mylist.map, but it doesn't. It wants you to put a constructor. So I don't know. Does that help?
Yeah, well, I think one thing is like distinguishing between tactics and constructors. Like, I don't even remember if REFL is a tactic or a constructor.
Yeah. Okay, fair enough. You will be able to tell it. So REFL is both a tactic and a and a function. There is a definition in the global namespace called REFL, and it is actually, the actual constructor of eq is called eq.refl, and it also has an explicit argument a. REFL is the short version of eq.refl, and it also takes a implicitly, so you don't have to supply it, and so you just write REFL, and then it's proving anything is equal to the same thing. But this is not going to work if you're trying to prove, something else is reflexive. This is only for equality. There is also a tactic called REFL. You'll be able to tell the difference on my screen because it'll show up purple when it's a tactic. Purple is for keywords, and all tactics are basically keywords in their position. So this is the tactic REFL, which proves anything by reflexivity, including equality. So yes, and then if I used exact, now this is the term REFL again. And you can see that docstrings change. They are actually separate things. You can tell the difference between them based on where they appeared inside the term. So this is sort of the difference between term mode and tactic mode, but there's this sort of deliberate conflation of, there are very many syntaxes which are shared and have the same syntax so that you can kind of transfer knowledge. That's the idea, at least.
Mm. Thank you.
Was there a way to reduce the goal by definitional equality so that you could see that this is REFL before actually typing it?
Yeah. So, right. So I mentioned that this is a sort of Agda style proof, but there are also, I would say that the more traditional way of proving this in Lean would be to throw some more unfolding definitions at it first. So here we could, simp with map, and then it unfolds the definition. Now we can see that it's definitely REFL, right? In this case, if we simp with map, then we get, well, it unfolded the cons, but we still have the length. So we also want to simp with length here. actually it did two things here. It did simplify the length away, but it also simplified away the +1. So now we no longer, like, this proof isn't actually going to work anymore because the Conger arc part has actually been removed. So it's just an application of the inductive hypothesis. So yeah, I'll show another version of this proof further down. Yeah, you can use simp in order to do clarification of the thing. There are a bunch of definition unfolding. There's also dsimp, which would help here if we wanted to avoid that thing where it canceled the +1s. Now it's just doing definitional simplifications. Okay, so I'm going to.
So if you remove the dot before nil and cons, does that mean something different?
Let me have both versions on the screen at the same time. Say that again?
So if you remove the dots before nil and cons,
Then
does
dot
that mean something different?
Before nil and cons. Yes. Oh no, since I'm in the namespace, yeah, it would resolve to mylist.nil anyway. So yeah, we don't need the dot. In this case, the dot means that it will resolve even if I wasn't in the namespace. But in this case, since I am in namespace mylist, it's still resolved.
When there are two options of a dot, like it can be list and my list, does it complain that this dot can't solve for you?
The dot is never going to be ambiguous in that sense. So in the dot you have the expected type. If the expected type is not available, the dot doesn't work at all. It just
Okay.
fails immediately. If the expected type is available, then it looks at that, like the head of that, and it's going to be something like mylist A or something like that, and then it looks for mylist.nil, and if it doesn't find it, then it errors. So there's always exactly one choice for where it's supposed to be looking. Okay. So let's do some more sort of realistic proofs using K-split. So here's an example theorem. So n plus 1 minus 1 is n by reflexivity. That's because the definition of subtraction on the natural numbers is a K-split on the 0 and the successor case. And in the successor case, it just returns the value. So, but the other way around is not true. So if I do n minus 1 plus 1, I don't get back to n. And the reason is because this is not integer subtraction, this is natural number subtraction. And at 0, it will sort of saturate and hit 0 again. So 0 minus 1 is 0. So if I do 0 minus 1 plus 1, I get 1, which is not 0. But if n is not 0, then it is the case that n minus 1 plus 1 is n. So let's try to prove that. So first I'm going to introduce this hypothesis that n is not 0. And then I call the cases tactic. So the cases tactic is going to split n into the two possibilities. One of them is 0, and the other one is n plus 1. In the first case, I have a hypothesis. So you notice that it sort of rewrites everything in my goal where the n's were and put 0 in there. So that's sort of what cases does. And now I have a hypothesis that says 0 is not equal to 0. And so that's what I'm going to use in order to conclude that this is an impossible case, right? Ex falso is a very simple tactic that just replaces the goal with false, just sort of simplifies things a little bit. Because I'm not, I could try to, well, I don't know, this thing here is not true, but I just don't care about it. So I just want to replace it with false. And then apply h0 is this not equal is the same thing as 0 equals 0 implies false, so I can apply h0, and now my goal is to prove 0 equals 0, which is true by Russell. In the second case, we have this thing, n plus 1 minus 1 plus 1 is the same as n plus 1. And this is true because it's a special case of this n plus 1 minus 1 equals n business. So this n plus 1 minus 1 cancels and becomes n plus 1. And since that's definitional, we can just prove the whole thing by Russell. Okay, so that's doing this with cases, and the main thing I wanted to show was just how how pattern matches and what we get here. Induction is almost the same as cases, but you see that it gives a slightly different subgoal. So in cases, we got a 0 and an n plus 1 case. In induction, we also get a 0 and an n plus 1 case, but we have an additional hypothesis here, which is that whatever we were trying to prove is true for the lower value, right? So our 0 case is the same, and our successor case, we can use this case tactic in order to say, I want to prove specifically the successor case, and also I want to name them, because right now they're named like these funny inaccessible things. And so I want to name them N and the inductive hypothesis IH. And so now I have this state. Now I'm not actually going to use IH in this goal because this was proved by case analysis, not by induction. So we just use riffle here. But just a basic example of what induction does to your goal. Okay, so here's a more interesting example of induction. So I'm going to define this function foo, which at 0 is 0, and at n plus 1, it calls foo of n, and then adds 1. And so if you think about it a little bit, you'll realize that this is actually just a fancy way of writing the identity function. So we should be able to prove that. So I have a goal that says foo n equals n, and we'll prove it by induction on n. And here I'm using the more extended syntax where I give it the two cases with these bars, and I get to name the hypotheses at the same time. So in the 0 case, foo of 0 equals 0. This is true by ruffle, but instead of proving it by ruffle, we can use simp in order to unfold foo. But I mean, once it unfolds foo, then it sees that 0 equals 0, and so it closes the goal. We can simp with foo on this side as well, and like before, it unfolds foo and then also cancels the plus 1. So we just get foo n equals n, and we can apply the inductive hypothesis.
Can you do for simplification without we put a name foo?
With the name foo?
Without it.
Without the name foo. If I simplify without foo, then it sees this foo application, and it doesn't know what to do with it. There's nothing, there's nothing else to simplify in the goal. It doesn't unfold definitions unless you tell it you want it to unfold. I can put simp on the definition, and now I'm basically telling whenever you run simp, always consider foo as something you can unfold. And so it's effectively like I put foo into every simp call after this. And so now this will work. Okay. I can also, since I simplified with everything and then I got to this point where I could close with IH, I can also put IH in here, and that will work. I can also use star, which, as I mentioned last week, simplifies with all local hypotheses, including IH, which is sitting right here.
But not full, you still have.
I still have,
Yeah.
because I didn't keep the add simp here. So we're unfolding. And so that means that actually I can compress this whole thing, because now I can make them sort of look the same, like all sub-goals. I'm just going to do simp, foo, and everything. And so I can make use of the semicolon combinator here in order to say, do induction, you get two sub-goals, run simp. And so this is actually what I would call the lean style proof of the same result. Rather than, writing a term level proof, we would just sort of call induction once and then use simp with the stuff, and it goes away. So it's very useful. Okay. And similarly, so the length map theorem from before, I can, rather than doing this kind of proof, because the proof amounts to unfold map, unfold length, and then use the inductive hypothesis, I can just write simp map length and star, and I can just prove it in one line using this trick. Okay. Okay, any more questions? Alright. Actually, I think now's probably a good time to take a break. So we're at an hour, so we'll get back here in 10 minutes.
Is there a way to get to use all the functional properties?
Eller samma grej flera gånger.
Um,
Försöker picka in for export.
It does work. Does it work? It does work.
Does DC
It's called-
exclamation mark exist also?
Yes. The star is not allowed for decent exclamation mark, but yes. It doesn't make much sense to use hypotheses when you're doing definitional.
Right.
Yeah, that's why it doesn't spell star first. Yeah,
because
auto
the
unfold.
hypotheses are never
Yes.
Oh, auto unfold equals true.
Yeah. So simp bang is shorthand for simp with auto unfold equals true.
Right. So if you want it to be kind of like Agda with control you or whatever.
Oh, I see. Is that what this does?
Then DC exclamation mark would do that.
Yeah.
Yeah, I mean, I guess like we just started with just finished in mind, so yeah, we kind of have to. I don't know. Actually, I feel like those are the nicest moments because it's still like you can just like talk about anything. Like, oh, it would be cool to do this or we'll do that. Instead, when you like are actually doing things and maybe like you're getting like results out of it, then those are the awkward moments because then they expect something and like you don't have it.
So
I feel like
wonder
expect.
when is there some kind of like generic proof search kind of like auto in Agda?
Um,
Anything special, just
I mean,
maybe if you want more
the answer is basically there are many, and I'm trying to figure out which one would be the closest to what you're thinking.
Yeah, I'm thinking something that does not take parameters and can work on like many different things. Kind of.
Yeah, so
Or that doesn't.
there's two main things that I could suggest. One of them is ASOP.
Mm-hmm.
This is a sort of general, so it will like or break up implications and ors and that kind of thing, and it will also do simp and various kinds of tableau proving methods. So,
Right.
so it's like Isabel Otto, I think, and.
Yeah, I also
you
assume
can get
there
a
is
bunch
not
of stuff.
a thing exactly like Agda's auto because the point of that is that it's supposed to run interactively, so it's okay if it takes several seconds to run.
Oh yeah, I mean there are plenty of tactics here that can take several seconds, and there are also a lot of tactics which actually does it work on this? Whether it's
Maybe no.
Maybe.
it broke the. I don't actually use this very much, so I do need to learn how to use it properly.
Another question I have is there a way of like recursively unfolding all constructors in the hypothesis. Like, for example, I was trying to prove do the homework or the exercises and wondered, like, is there a way to just say unfold everything so everything becomes a hypothesis directly, kind of.
I think I think this is the answer to your question, but I need to have an example which actually demonstrates it. Let's say that I have H is two is something we can't prove, and then does this work? Does not work. Does this work? Oh, do I have to do? I'm surprised that this doesn't work actually. So that basically does the job, but it does require you to say what kind of constructor.
Yeah,
you
okay,
want
but
to hire.
that's fine, I think. Did it work now? Yeah.
Yeah.
Oh, I never seen this case in Leaf.
Yeah,
Oh.
I tried some, and you can do it with all. You can do,
Like this.
yeah, or
Or with,
be
with,
more-
with all goals you.
yeah, but yeah, that's the same thing. And you can replace trivial with hypothesis. I assume.
Well, in this case.
Oh right, yeah, oh, right. We don't.
Maybe
we don't have a
let's
goal
say
like that.
we wanted to do P.
Oh, I'll P.
No, P. You can do P
Well,
and
that
Q
would-
to make it more interesting.
P and Q.
And have the Q in H2. Have both cases be Q in H2.
Q like that.
Yeah, and P in H. I meant.
Well, because we need to have a Q on all the sides.
Yeah, I meant H should be P or P, H2 should be Q or Q, and then
Oh, I see.
Phrasal.
P and Q. Just to tell it like.
Yeah.
Oh yeah.
Oh.
Right, and now we also need the constructor.
No, actually, it seems
Oh,
to be
it unfolds the.
Trivial seems to be smarter than I thought.
Right.
So you're
goal?
no.
So I found one from last year.
No, I'm curious.
That was kind of nice.
Like yours from last year.
Yeah, I found mine from last year. That was kind of nice because I made some.
You could also
Yeah, I should.
do
goals,
the.
and I had like
Just
done most of
print.
those things.
And show
Yeah, I don't know. Maybe there's even like extra questions like
Okay. I mean,
how
there aren't
have you
many options, I
contributed
suppose.
to
Yeah.
work
That one
environment,
I like I don't know.
academic citizenship? Yeah.
I'm assuming that if you do
Yeah,
the
but
try
it's
this,
like
it
I
will
went
if you actually
to work
insert
in
the try this, it will
that
complain when you have the dagger.
citizenship.
so.
Oh,
Yeah,
explicitly
but maybe I just wanted to
uses
say-
and.
Yeah.
Yeah, I guess that's nice
You know,
because it's
help me.
like pretty common that you have some and.
Yeah,
and you
some
go.
and of trivial things.
There's that you could like
And the trivial things can be,
and like when you're talking
well,
about
it can be
it's
literally
it's
true
very
and true,
nice.
which is
Yeah.
trivial.
Yeah,
But it can also be
I was
assumption
reading
or
last year.
contradiction, which is like you've got P and not P in your context.
But if you have or in the goal, it's
Right, like, what is
trickier.
the
Then you would need to do some
thing you
uh,
tackle.
like.
What's the-
If I could prove ors,
I think
if it was
going from ideas to like actually something.
well, yeah, I guess. Oh no, I think this will work.
When you never,
This.
No.
No.
No, it's just when she sent the thing.
Oh no, because it has to apply and intro. Oh, but if I had an and here, then that would.
Oh.
Yeah,
that's
in
for
the email where she had like
Yeah.
the
Yeah.
spreadsheet.
But if you
with
have just
lines.
the or,
Just the or.
No.
Well, I mean, if I had this, then I think that would work. Because this is the side.
so what does this? Oh, right, that's for the decidable.
Yeah, so if it's able to infer a decidable instance, and this is an equality of natural numbers and orders and stuff, so that's easy. So then it can solve it. Okay, but looks like it's
And
time.
for
I mean, I think
for
like
induction is better way without we have to explicitly put the case.
so that's right.
Above you have to
Something about
put
what you're
This?
saying.
no. I think above you wait when you explain. Yes, you have to always put that match on case.
So you don't have to. You can also do something like you can use this,
But in induction, maybe there is no.
but you have
Easy way
variables
to-
that you want to name. So if you don't,
Okay.
well, I mean, I guess in this case
Yes,
you don't need to name
yeah,
them.
yes.
So if you don't need to name them, then you can just use the dots. And
No
that's
problem is
Oh,
that
it's
we
like
have
if
it
you
to
have another
name if
dot.
induction.
yeah, but if you wanted to
Because
use the induction hypothesis right here, then
Yes.
you would need a name.
I think it's
Yeah, that
I
works.
think it's just paid.
Um,
Or like if you
Because it's CCN kit cannot
then you
generate
have to register that
a name
in,
for your
yeah, exactly. So this,
um,
yeah, unless you use
in Primula,
other methods to refer to the name, you won't be able to refer to it
so like,
as long as it's here as this little A.
yeah,
The dagger means it's not nameable.
Yeah.
Like,
Maybe asked,
you have to name it first.
But how did it know that it was the induction hypothesis you wanted when you used the case underscore IH? Or oh, maybe.
The first underscore is the name of the case, and then after that is all of the variables that you want to name in reverse order.
It's in reverse. Oh, that's nice. Okay.
That turns out to work well in general when you don't know what you ran a command, but you don't know how many things it introduced.
Yeah.
So it just took the last 10 things. But okay, let's get back to it. So here I wanted to show you the match tactic, which, like many of these cases, it looks the same as the match expression. So this was the match expression. There's also match tactic, has the same syntax, you write match and whatever, except that the arrow, the stuff after the arrows is a tactic instead of a term. So now you notice the color of the ruffle changes. This is the one ruffle, this is the tactic ruffle. And this is not working because this is a term. So if I want to explicitly use a term, I use exact. That's now this is syntactically correct again. Match also allows you to do multiple matches and overlapping patterns. So here I'm writing a function which gets the first sum in, I give it two options and I want to get the first sum. So if the first thing is a sum, then I return that. If the second thing is a sum, I return that. If they're both none, then it's none. It does do exhaustiveness checking. So in this case, the none case is missing, so it complains. You can also, if two cases, like in here we have two cases that look the same, so we can just use two bars like this, sum x or none, or none, sum x. That works the same. The same sort of pattern matching infrastructure, we've already seen it used to make definitions like this length here, where you leave off, notice that there's no colon equals here, you leave off the colon equals and then you leave off the match line. You can also use fun, so I guess you could leave them both off here. But if you use fun, then it's creating a function type. So here, the target type is a function from option to option, and I just give it exactly the same syntax, but I'm not matching anything, I'm matching on the arguments. And the tactic version of fun is called intro, but otherwise exactly the same syntax, modulo the fact that in here we have more tactics, so it's got to have exact. All right, so inductive types can also be propositions. So here I have two types. They look almost identical. I've called them inhabited and non-empty for reasons that we'll get to in a sec. But one of them, you give it an element of type alpha and it produces a my inhabited alpha, and this is the type. The other one, I give it an alpha and I give it my non-empty of alpha, and this is the prop. So the difference between them is, well, I can define this my inhabited.get. So here this is just like all the functions we were writing before. We pattern match on our my inhabited, we get A, and then we return it. So this, given a my inhabited of A, we get an A. And we can also prove that if you given A, you construct a my inhabited, you call get on it, that's the same as the original. And that's just true by definition of how we wrote this down. But if we do exactly the same thing for my non-empty, it fails. It gives a slightly confusing error, I think. But among the things that it mentions, it says the Kazan can only eliminate into prop. And this hints at the differences between the recursors or the eliminators. So let me show you here. So we have we have my inhabited.rec and my non-empty.rec, and there's some minor notational differences which you should be ignoring, but the important part is the fact that the motive here, it says motive, my inhabited to sort u, and here motive goes to prop. And so what that means is when you define this inductive type, you only get a recursor that allows you to construct proofs. So this is a proof thing, and it only constructs more proofs. So I can't construct this get function because the get function returns an alpha, and alpha is a type. It's not a proof. So that fails. However, I can write basically the same thing, but to prove a theorem instead of a definition. So if I wanted to prove, for instance, that there exists an element of alpha which is equal to itself, then I can do so by doing this pattern match, and everything works. So here, I have to prove that there exists an X, and I have an A of type alpha. So I just give it the alpha, and then this is a proof that, A is equal to A.
Why it didn't work in this get?
So this is the resulting type here is alpha colon type. If it was true, then this works. If it's unit, then it doesn't work. If it's not, then it doesn't work. If it's false, then it works. So the difference between these is if the target type is false or true, or there exists an X such that whatever, or an or, all of those are propositions, and so it will work. But if it's a NAT, or a pair of Booleans, or a unit, or any of those things, those are all types, and so it doesn't work. Okay. Alright, so I actually wanted to demonstrate that this is actually critical for soundness. That it would not be allowed if let's suppose that Liam did allow this definition. What would happen? Okay, well we would get a definition that had this type, my non-empty n to alpha to alpha, but in particular it'll work for n. So we have a function from my non-empty n to n, and moreover, presumably it would have the same property here that my inhabited had. That when we run it on an argument, we get the value back. So if we given any a of type n, we construct my non-empty of it and then call get on that, we would get n back. Well, if there exists a function with those properties, then we can prove a contradiction. What's the idea? Well, we can construct a and b, which are we'll construct a my non-empty in two different ways. One of them we use 0, and in the other one we use 1. The key property is this here, that A and B, despite the fact that they were constructed differently and they look quite different, they are actually definitionally equal according to Lean. Why? Because they're both proofs. Because my non-empty was declared at the beginning to be a prop. So these two are already definitionally equal. But get of A is equal to 0 because we assumed this hget property. And similarly, get of B is equal to 1, but A and B are the same thing. So 0 is equal to 1, and that's bad. So now is the time when I tell you about a function that has exactly the type that I mentioned. So let me introduce you to a function called classical.choice. This function has the type non-empty alpha to alpha. So it's like this get function. It allows you to invert non-empty. And so I've sort of given you a hint as to why this is sort of weird, that you should not be able to construct functions going out of this, because a non-empty essentially collapses all of the data in the type alpha into just one, it was non-empty. It's, there's only one way for alpha to be non-empty. And this is, given a proof that something is non-empty, we get an element back. But the point is, the reason why we don't get false out of this is that the hget property fails. Given a non-empty intro, you apply classical.choice to it and you get the element back. That's not true. And this is not a provable theorem. In fact, it's disprovable using exactly this strategy. Okay, so inductive types can also be predicates. So you can have an inductive type that has an index. So this argument here, we call it an index, and here we're going to construct an inductive type, which is a proposition, but it classifies evenness. So it's going to, given a natural number, is even of that natural number is a true proposition when that number is even, and it's a false proposition when that number is not even. And the way we do it is we have a constructor for 0. So 0 is an even number, and then if we have an even number, then adding 2 to that number makes another even number. Okay? So I'm going to comment all this out and do the proof in front of you so that hopefully you can see how we work with these proofs. So what I want to prove in this situation is that is even n is equivalent to, there exists a case such that n is equal to 2 times k. Okay, so this is another way that, this is sort of the normal way that people write even, but we've defined this funny inductive type, and we want to prove that that's really classifying the same thing. So we have two goals. One of them is to prove is even to this exists, and the other one is exist is even. In the first case, we have an implication, so we can introduce it, and then we can do induction on it, because it's an inductive type. We have two cases. One of them is 0, and let me get back to something not broken. So one of them is 0, and the other one is 2. And in the 0 case, we have to prove that 0, there exists a case that 0 is equal to 2 times that number. So we can use exists, so the exists tactic, I mentioned it very briefly, but you can give it the thing you want to inhabit the exists. In this case, obviously, I want to inhabit it with half of this number, which is also 0. So I use 0, and actually close the goal because the second part is just 0 equals 2 times 0, which is true by definition. So that's the base case. And then here we have, maybe I should call it n. So we have some n, and then we have a proof that it's even, and then we have an inductive hypothesis. Okay? And we want to prove that the induction hypothesis holds one more. And so a way to do that is we can destruct this induction hypothesis. And we could use cases for this, but instead of using cases, I will use let, which gives us this slightly nicer syntax. Case. And so you can see that we have exists k such that n equals 2 times k has been broken up into 2 pieces. We get this equality, and and we want to inhabit now this existence with k plus 1, right? So if we know that n is equal to 2 times k, then the k that we want to prove this is k plus 1, because then n plus 2 is 2 times k plus 2, which is 2 times k plus 1. So if we rewrite with eq here, then now we have to prove 2 times k plus 2 is equal to 2 times k plus 1, which is true by ring. So ring is, if you recall, this thing that proves things about polynomials, and this is a true property of polynomials, so nice. And that's the first half of the proof. There's a second half of the proof, which is going the other direction. So we have, there exists a case such n equals 2 times k. We want to prove it is even of n. We'll use intro with pattern matching this time. We get two things. And we can rewrite with this equality again. And then we can do induction. So we do induction on k this time, which is also an inductor type, natural numbers, which has two cases, 0 and successor. In the 0 case, we want to prove is even of 2 times 0. And since this will be true by definition, but just to remind you, this is the same as is even of 0. So I can write it like that. And constructor, of course, we'll find the constructor that applies in this situation, which is the 0 constructor. And then on the other case, we have an inductive hypothesis. And I think, and now we have something interesting. So our inductive hypothesis is sort of funky. We know that n, maybe I should call this n. Let's call that k. So we know that n is equal to 2 times k plus 1. And we have an inductive hypothesis that says, well, if n was 2 times k, then we'd know that 2 times k was even. We can actually apply constructor in the situation. Maybe I should simplify first. Simple. No. I want to rewrite with a proof that 2 times k plus 1 equals 2 times k plus 2 by ring. So now we have 2 times k plus 2, and now when I apply a constructor, it just gives me 2 times k instead of something weird. We're sort of going to get stuck here, right? I apply IH, and now I want to prove that n is 2 times k. I know that n is 2 times k plus 1, and this is not a provable goal. What happened? Well, this has to do with how induction tactic works. Induction, when I ran it, it had this goal that said is even 2 times k, but it had this hypothesis, EQ, n equals 2 times k. And then I did induction on k. What it did was it looked at my whole goal, everything that depends on k, and then sort of reverts, and it uses that information. So it's like, revert, by the way, is sort of the opposite of intro. It unassumes something. And it reverted this hypothesis that n equals 2 times k. And that's bad in this case. We actually we want to forget about this assumption entirely. So for that, we have the clear tactic. Clear tactic just deletes a hypothesis from your context. After having done so, our context is clean and only says is even of 2 times k, and this works properly. And so now our inductive hypothesis just says that is even of 2 times k, and we don't get stuck. So after this apply, we're actually done. And done the same as done. Okay, so that's the proof. All right. Any questions?
Can induction works with if a function has two arguments?
Induction will work on, when you pass induction something, this something should be an inductive type. And it will do induction on that inductive type. I don't believe it works on. There are reasons why you can pass multiple things in here, but generally speaking, it'll only be one thing. Even if it's got like like this is even, we're going or like here we did induction on the hypothesis that n was even. We're not doing induction on n. We just passed the one thing, that the inductive type itself. All right. And now I get to show you all of the definitions of the propositional connectives and reveal that actually everything was inductive types all along, in case you haven't figured that out already, or is an inductive type that has two constructors, one of which is a proof of A, the other one is a proof of B. Exists is also an inductive type that has one constructor, which has a proof, a witness, and then a proof that P holds for that witness. True is an inductive type that has one constructor, which is true intro, also known as trivial. False is an inductive type that has no constructors at all. So the recursor for this says, well, if you prove something for all of the zero constructors of this type, then whatever you want holds. So that's the principle of explosion. And is not an inductive type, though. It's a structure, and that's actually what I want to talk about in the next section. But let me tell you, a structure is really a kind of inductive type. So and is also an inductive type. For all is actually not an inductive type. It's a dependent arrow, which is a part of dependent type theory. It's just a core of the language. Okay, so what's a structure? So a structure is a inductive type with one constructor, more or less. So it basically comes with a few extra features that make it easier to use. But from the perspective of Leem's kernel, it is really just an inductive type. So here's how you declare a structure. So structures are basically kind of product types. Here I'm making like a two-dimensional point. So I give it x and a y that are numbers, and then we get a point that is a two-dimensional number. So we say structure, point, where, and then we give it fields, and we don't put bars here, which is just the types of the fields. And that's sort of equivalent to this kind of inductive. So not multiple constructors, but just one constructor called make, or mk, I should say. And all of the fields of the structure become the binders in this make, which this is a function of 2 point. I just want to briefly mention that there is actually a way of suppose you didn't want it to be named make, if you want it to be named make and you not, charging by the letter, then you can do it this way using this double colon syntax right at the beginning of the structure. And so you'll see this sometimes in structures. The other main reason people use this is so that they can attach docstrings to that function, because otherwise it's not available in the syntax. But okay, whatever. So you can construct a point using the .mk function, just like you would with an inductive, because it is actually just sugar for an inductive. You can also pattern match on it, just like an inductive. So we pattern match here. I'm pattern matching on a point, mk of a and b, and we get the pair a because we want to return them. One thing that you don't get with inductives, at least not by default, you'll see these functions don't exist for a point prime, but we have a function from a point to natural numbers called x. So basically for each of the fields of the structure, we got an additional function that is taking an element of the thing and pulling out that thing. We call it a projection function. You can, however, define these pretty easily, and this is roughly speaking what these definitions actually are. Is you just pattern match on it and you pull out one of the elements in this make. There are a few extra things that you get with structures. So you can use this syntax called a structure instance, and you give it the names of the fields. So you use these braces, and then you use the name of the field, colon equals, and then the value. And this constructs a point here. So we have a point 0, 1. And there's also a shorthand syntax for this where these are backslash left angle, whatever. And this allows you to construct a point like that. So sort of like a triple syntax. You might also sometimes see this. So like if you're defining a function like this, then instead of writing colon equals, you write where, and this is just the same as if you put the whole thing in braces, like that. Okay. Any questions?
Do you get eta equality constructions?
Sorry, say that again?
Do you get eta equality?
Okay, eta equality. Yes. Yes. Those are done not by being a structure literally though, but so basically the kernel detects inductive types that look like they might have been generated by the structure command, and eta applies to those. So.
Can you disable it?
I don't think so, actually. It's not really something that Lean doesn't really have flags at that level normally. Okay.
Is the double colon used for something else, or is it just for declaring constructor names?
This double colon here is used only in this specific location. Otherwise, Lean doesn't really use the double colon, except that it's the notation of list concatenation. So this usage of the double colon has nothing whatsoever to do with list concatenation, or sorry, list cons.
Mm-hmm.
But that's normally where you'll see the double colon, is list cons.
Why is exists not defined as a struct? It also has only one constructor.
Because even though it is a one constructor, it is also a prop. And so one of the things, actually, maybe we can just test it. So let's say that we wanted to make exists like that. It's a structure, and so we just need to make these the pieces like that. Aha! And we get an error. It says failed to generate projections for a prop structure. Field W is not approved. And you can kind of see what the issue is. What it's trying to do is define exactly that kind of get function that we were writing up here. It tries to do, so like I said, structures have both the inductive type and also a couple extra functions, which are these projection functions. And so if Lean gets very mad at you if it's not able to define those functions. Yeah. So that's why you can't make it a structure. But even though it is a prop, the fields of and are also props. So A and B are props, and it constructs a prop. So when Lean tries to write down the pattern match and get out the first thing, it works. And so it says, yes, this is a perfectly valid structure, because even though it is a prop, the projections still work. Okay. So and is a structure. And if and only if is also a structure. Structures can also do this extends thing. So you can write extends and then another structure or a list of structures. And what it's doing is essentially merging together all of the fields of the structures of the things that came from. Although more precisely what it does in this case is it adds a field called toPoint, which is a point. So a point 3 is really just a pair of a point and an natural number. And that explains why when you want to construct a point 3, you can't write it like this. You have to write it like this, because this is the construction of a point, and then this is the construction of the point 3. I don't really recommend that you write like this, though. This is much clearer, and it also erases that sort of details of how this thing is encoded. You can just specify x and y and z, and these are the pieces. But you could also specify 2 point, because 2 point is actually the name of one of the fields. So if you do something like this, for instance, and that would work. Okay, and then one other bit of extra syntax that you get with this extends is that I can just write point3.x, and it acts the same as if I had point3.toPoint.x, which is what it really is. Okay. As you might expect, since this is dependent type theory, we can also have dependent fields. So here we have a point like a checkerboard point. So we have 2 natural numbers, but then we want to say that the points live on some kind of checkerboard pattern, so we'll say that x plus y is even. And so, for instance, 1, 1 will be one of our checker points, but 1, 0 will not be a checker point. And so here we just write is even, and then we're using x and y, which are these previous fields. And then when we're constructing one, we give it x and y, and then here we have to prove that 1 plus 1 is even, so we give it a proof. Okay, so yeah, now we understand why and is a structure, and also subtype. So we have not looked at subtype yet, but subtype has a value and a property, and the idea is you give it a predicate, and it's an element of alpha such that the property holds. And we think of it as like a subtype or like a subset of a set. So if we have like the set of natural number, these are natural numbers which are greater than 3, right? So if I want to construct an element of this set, well, one of them is 5. So I'll say I construct an element of this subtype, which is a structure, so I have to use these angle brackets. The first thing I give it is 5, and the second thing is a proof that 5 is greater than 3, which we can do by aside. And then similarly, we can sort of get stuff out of this using those projections called val and property. So if I have an element of this set of natural numbers which are greater than 3, then its value is not 0, because so here we can write value not 0, and then to the property, a dot property is a proof that a dot val is greater than 3, so therefore a dot val is not equal to 0 by linear arithmetic. So doing some linear arithmetic, we can figure out that one of them applies the other. Alright, so our last topic for today is type classes. So the syntax for type classes is very similar to for structure. You just replace the word structure with class, and that's basically the same as this here. So this is an attribute. It's just modifying some additional data structure, but otherwise it's exactly the same as a structure. So what is the difference? And it also it pairs with this other thing, which are type class implicit arguments. So those are represented with these square brackets. So here I'm going to define a function, sort of like our point.x function. Given an origin, it'll return a natural number. And so we pattern match, we get out the x, and we return it. So we can construct one of these just like a structure, because it is a structure. Here we want to construct an origin, 0, 0. And so point.x and origin.x have basically the same type signature, although one of them is using the square brackets and one of them is using the round brackets. But we can see sort of, what the difference is. When you try to apply origin x, we should give it an origin, right? I try to pass in my origin, it doesn't work, because it's actually not expecting an argument because it is implicit. So I have to pass the @ sign in order to say pass the thing. But we can just use it like a function, like this, just like point.x. So here we had pt, which was some previous point, and here we have my origin, which is a previous origin. We apply a function. So it's basically the same, except one of them is taking the argument implicitly. But now this is sort of funny, right? Because we wouldn't expect, when you apply point.x to just not, underscore, it's not going to what.x, right? There are lots of points. Which one do you want to pass? And similarly, if we have origin x and we don't pass it an argument, and that's sort of what we get when we write it like this, then it's just going to fail, right? So what's the idea? Well, the difference is when it's a type class, it's going to try looking around in your context for things of the right type. So here, point.x, there's a point in context. It could be using it. It could write here point, but it's not. It just says, I don't know. Whereas here, it actually just, it notices that there's an origin and it's looking for one, so it just uses it. And so this is sort of the normal way you use type classes. Although there's one extra thing that makes this more useful than just looking through your context, which is that you can have instances. So you can write instance instead of def. And that's, again, the same as using an attribute. The instance on a regular def. Here I want to say, so like before I said my origin, I'm going to define 0, 0 is an origin, but I'm going to mark it as an instance. And now, it doesn't even have to be in my context. Now it's just searching the library, basically, for all of the instances, and since it knows that there is an origin somewhere, it's going to use that. So this is actually applying origin x to my origin. Okay, so this is not completely trivial, because you can actually use this to chain proofs together. So for instance, I showed you the isEven function, isEven is an inductive type with these two constructors. And I can make this into a class. I'll say isEven is a class. This is sort of, this attribute here is sort of a post hoc applying attributes to things. So I'm going to make isEven into a class. I'm going to make isEven.0 into an instance. I'm going to make isEven.add2 into an instance as well, but I have to slightly change the type signature because here isEven is taken as a regular argument and I want it to be taken with the square bracket arguments. So once I make these two instances, now if I do isEven of 42, it can actually prove that by applying isEven.add2 21 times to 0. And it just does that all in one go. If I, wait for me to look at that. I look at T, I believe I will even be able to tell that it has applied isEven.add2 a whole bunch of times. It just keeps going, right? So it was able to construct that proof by a sort of back chaining search of all of the instances. And so that's the real use of type class inference. And Lean and MATLib uses type classes everywhere. This is super common. One of the uses of type classes is for notation. So let's say that I wanted to be able to write A times B. I've used this several times for like natural numbers and stuff, but it's actually a generic thing. So if I had a type alpha, which has the mul type class, then I can write the star between elements A and B. We can actually see that the definition of mul is quite simple. It's just mul is you have a function alpha to alpha to alpha, and you supply that, and now you have the ability to multiply stuff on this type alpha. And using extends, we can construct a type with a multiplication that has additional properties. So for instance, here I can define semigroup to be something that extends them all and also has an associativity. So A times B times C equals A times B times C with the different parentheses. And so that's how you can define a class like semigroup. You can define an instance like this. So natural numbers are a semigroup because they have, well, they already have a mul. That's the one that I've been using the whole time. But I can prove this assuc using that mul assuc. And now, if I have a generic theorem, I can prove a thing about any semigroup. Like, for instance, it has four-way associativity. So if I have four things, then I can associate them all from the left to the right by using a sock twice. And these applications work because here I'm not supplying this my semigroup. It's just sort of figured out by looking through the context using this type class search mechanism that I wanted this alpha to be the semigroup. I wanted this semigroup to be the one that supplies the multiplication that's happening right here. All of that is happening through type class inference. And then in this example, well, now I can use it to prove theorems about natural numbers, like this one here, where 5 times x times 2 plus y times y, where these are natural numbers, I can swap around the associativity by applying a suc4. So that's all how that works. And we don't have time, so this is where I think I'm gonna stop. So I might show you just a little bit of like what real world type classes look like. So this is the definition of monoid, which extends a semigroup. This is the real definition of semigroup, which otherwise looks pretty similar to what we did. Has some projecteds and stuff. There are some default arguments here, some additional fields, multiple inheritance, this kind of thing. But at its core, we've really seen all of the features pretty much that are being used in this definition. So that's what I wanted to show. So we will be meeting next Tuesday, and have fun.
I just asked one more thing about the prop versus type. Like, I was a bit confused why all the propositional constructors or types were props. Like, because a prop is just a true or false statement, right? So why would and like my intuition says that you shouldn't be able to like extract the fields from an and, for instance, if it's a prop. Like, I'm a bit confused.
Yeah, so the idea is that a prop is something that can be true in at most one way. And since there's only one way for an and to be true, there is basically exactly one thing that you can take out of that and to be the first thing, which is also true in at most one way, and for the second thing. So basically, because it's propositions into more propositions, there's no issues here. If it was propositions into something with more elements than a proposition, then there would be some potential for clashes. But basically, because it was propositions in and propositions out, we don't have any issues with this.
And what's the benefit of using a proposition other than kind of a syntactic? Like, is it more efficient for the?
Well, so there are versions of all of these things basically for both propositions and types. So and or are what you call them when they are over propositions, and sum and product are what you call them when they're over types. They have slightly different behaviors because of how one of them has this, there's only one way to be a proposition. It has proof of relevance, and the other one doesn't. But structurally, they are basically the same definition, looking exactly the same if you copy and paste.
So the advantage is that you get proof irrelevance, which can be useful in some cases, for example.
Yeah, it helps you represent things that you want to think of as propositions and not as actual data values. And it is also used by the compiler. So the compiler will erase proofs. So if you do some crazy proof of something, and it shows up as like a piece of your program that is calculating something, it doesn't have to run your proof. It just ignores the proof because all of the purpose of the proof was to validate that something or other holds. It's not actually trying to be data carrying.
And can you know like a priori generally with like, I don't know, like some kind of ad hoc intuition of if something should be a proper type, or sometimes do you ever run into a case where you make a mistake, or do you?
For the most part, it's like if it, there are certain, like and, for instance, there's no harm in it being a prop because it still has projections, right? Like you can make it be a prop and it doesn't lose any information, so it's sort of better in that sense for it to be a prop. Most of the time when you make definitions, they're going to, like, it depends on whether you want it to have many elements or to have only one element. So that's sort of where you get the intuition from. Like, is it supposed to be proofy or is it supposed to be like data? And I mean, there are a couple cases like typing derivations frequently show up as both. There's the concept of like, does this term have that type in some kind of proof system? And then there's also the concept of a derivation tree. One of them is like just a yes/no question, and the other one is a data object, which has like, how did you put together all of the things? And there are multiple ways to derive the same property and these sorts of things. So I would say from the mathematical side of things, it's very sort of clear which one, mathematicians will use completely different language to talk about the two different kinds of thing. So you probably won't get confused if you're on that side. If you're, deep into propositions as types and Curry-Howard and stuff, you might get confused about the difference. But I would say from the mathematical perspective, it's quite clear.